One of the applications of average rate of change that you're familiar with is average miles per hour, the average speed at which a car travels. As you go from Mount Vernon to Columbus, I mean, it's just downright near impossible to maintain a steady speed unless you want to go super slow. There are some places where the speed limit is 25 miles an hour. There's other places where you can go 55 and get on the interstate and go 70. So the point is that if we drew a graph of the time and the distance, you know, the distance divided by time, that's your speed or your velocity, right? So as you're working your way out of Mount Vernon, you're not going to get a lot of distance with your time, but then when you hit 36 South, you know, you're going to be able to go a little faster. If you're going to go through Centerburg, you go a little faster, then you're going to hit the interstate, and yeah, you're off your way. Now see, when we talk about average rate of change, if we wanted to figure out your average miles per hour in getting from Mount Vernon to the interstate, so you know the slope is changing as you go. Your speed changes, and once you get to the interstate, so let's just say this is the Polaris turnoff. So you've been on the interstate for about 10 miles, you're buzzing your way down to the Polaris turnoff from Sunbury. Well, the average rate of change, as I said before, the way we could figure that out is if we drew a straight line that connected these two dots, then that would tell us the average speed in going from Mount Vernon to the Polaris turnoff. Remember, the average rate of change is equal to the secant line that connects these 2 points. The secant line is the name of the line that mathematicians give for a straight line that connects 2 points on a curve. And so there you go. That's why excuse me. That's why I'm using the word secant. So if we were to figure out the average rate of change or the average speed, I would take the time and the distance here and the time and the distance there, and so that would be distance divided by time, or we would say that the average rate of change, or in this case the average velocity, would be the distance when you finished. You know, so that, what would we say that was? Polaris minus the distance where you started here at Mount Vernon, and that's going to be divided by the time that you got to Polaris minus the time that you started here in Mount Vernon. Okay, so it's changing the vertical, change in y over change in x, or change in the horizontal, or in this case change in time. And so that's going to be your average rate of change. Let's go back to a function. I worked one out here. If we use the function f of x equals x cubed minus 13x plus 12. Let me draw you a sketch of this so you can kind of see what it's doing. I went ahead and factored this, and I'll do that in a minute, but just for now I want you to see just a little sketch of this. Let's see. We are going to cross the x-axis at -4. It's also going to cross the x-axis at 1. It's also going to cross the x-axis at 3. And when x equals 0, the function is 12. So that's just for argument's sake. Let's say that's somewhere up here. Not to scale, but this is just going to be a sketch. The graph of this function is, again, just a sketch. It's going something like this. Okay? So it crosses the x-axis at those 3 points. It comes over the y-axis at 12. What I want us to do is I want to figure out the average rate of change between when x is equal to -1 and when x is equal to 2. So somewhere down here. Okay? What's the average rate of change between these 2 points on the function? So again, what we're really looking at is what is the slope. Oh, that wasn't very good. What is the slope of the straight line that connects these 2 points as I butcher my picture? Okay, there's a reason people invented a ruler. Might have been good to use there. So, if we want to figure out the average rate of change, that's if we call this f of x and x, the average rate of change, that's equal to the change in the function divided by the change in x, or the function at, let's pick a point. We're going from -1 to 2, so the function at 2 minus the function at -1, and divided by 2 minus -1. Well, you can check this for me, but if you put 2 into this function, you're going to get as your final result -6. And if you put -1 into this function, you'll get as your final result 24 for the value of the function. And the denominator is still 2 minus -1, which is 3. And -6 minus 24 is going to be -30. And so we expected it to be pretty steep, right? I mean, if the value of the function here is -6 and just 3 units over, the value of the function is 24. That's a drastic downhill. Well, sure enough, the average rate of change is -10. It's pretty similar to slope. Yep, because you're actually calculating the slope of the secant line, the straight line that connects the 2 points on the function. Hopefully that explains it for you.